Hi, this video is part of a course on food physics. The porous media framework in that food physics is part of the theory section. And then part of the theory is this poromechanics. And the poromechanics had a a number of sections, and this one simply summarizes all sections together. So when we want to understand deformation in food or compute deformation in food like shrinkage or swelling, the poromechanics framework comes in handy. It enables shrinkage and swelling in a mechanistic way, so we can understand these shrinkage or swelling from the fundamental principles. So poromechanics combines transport and deformation and solid mechanics, but all in the context of a porous medium. And the transport and mechanics gets coupled because, for example, evaporation would cause pressure generation, and that could lead to puffing of a food, or moisture loss that could lead to shrinkage. So those examples, like this one, it uses pressure to deform, and then this one shrinks due to moisture loss. That's how transport leads to deformation. And then deformation in turn affects the transport. As you see in these potatoes, for example, they're smaller, so transport would be in a different length scale. And then the bread is larger, so transport would be in a much larger size, so the transport gets affected. So the transport and mechanics are coupled. So by combining these two, it enables understanding of shrinkage and swelling from scratch. We can get porosity, and we can get transport also more realistically. So poromechanics adapts the equations of mechanics to porous media. And there are two particular aspects that we should make note of. One is these quantities like stress and strain that we are familiar with for mechanics. They are applied here in an average sense. They are averaged over some sort of a representative elementary volume. So that's one way it is different for the porous media. The other way is that when you have a load like this one on a porous media, note that the load would be shared by the solid matrix and the fluid. So load is going to be shared. So if we write the equations, then applied stress is equal to effective stress on solid skeleton and fluid pressure. And so from these equations, knowing the applied stress, we can relate effective stress on the solid skeleton to the fluid pressure. And where does fluid pressure come from? Fluid pressure is a volumetric average of the liquid pressure and the gas pressure that comes from transport computation. So how do we obtain this deformation? It is a complex process. So what is shown here is just a conceptual schematic. So first we find out what causes deformation, the driving forces like change in moisture or generation of gases like water vapor or carbon dioxide. So those are driving forces. We decide those first. Then we look at what type of material is it, and that comes from experiment. So this material model and the driving force are combined with the governing equation for solid mechanics, and we solve that to get what's called the deformation gradient, from which we can calculate displacement of the solid. So the displacement of the solid, from which we can get velocity of the solid, and this velocity of solid gets included in the transport equation. So the velocities that would normally be there in the transport equation, like Darcy velocities, get modified due to velocities of solid. So this is how we include, we obtain the deformation and then include it in transport, and we have sort of a coupled transport deformation system. And now here are some of the equations. It is hardly intended to be complete, and just a glimpse of the types of equations that we develop. So this first one is basically the equation of equilibrium, but for the porous media, that relates stress in the solid to the pressures in the fluid phase in the porous media. Now this stress, this one, is transformed for reasons of computation and so on into another type of stress. This one is first one is called Cauchy stress, and this one is called Piola-Kirchhoff stress. But that's not the point. The stress is transformed, so this is just a transformation, and then this particular stress is related to strain for the particular material, and the material aspect comes from the strain energy function given by W. That's for that material. So the stress is now related to this strain using some sort of a constitutive relation, and then the driving force is the fluid pressure, and that comes from transport, and that's how it couples with transport. Transport leads to the deformation. Now the equation is not solved even in this version. For example, the fluid has two parts, water and gases, and they're handled differently. We're not getting into those details. The main point is we now have this equation where the only unknown is F. So we solve for F, which is the deformation gradient, and that is related to strain. We're coming to in just a second. So we solve this for deformation gradient. Note that this is really the final or close to the final form of equation that we solve to get this deformation gradient. Now the deformation gradient F can be related to strain, and strain in turn can be related to displacement. So eventually we get, this is the quantity displacement that gives us how the solid in the food shrinks or swells, and so this is my entire process of computation, or the physics, how everything relates to each other. And the transport equations also get modified due to deformation, and a quick way, easy way to see this is in the transport equation, and here is the equation for water transport, those are derived separately in other modules. And in transport, this velocity that we see, that velocity of water is in relation to the solid. So this would be velocity of water in relation to the solid. But then the solid itself is moving. So we also have velocity of solid in relation to the ground. So this convective term that we have in the transport equation, it gets modified. So it now has two parts. One is the velocity of water or the fluid phase with respect to the solid, plus the flux that happens because of the deformation of the solid. So the transport gets modified because of the deformation. In another way to say this is that transport is coupling with deformation this way. So in the previous slide, we showed how transport affects deformation, and this one shows how deformation affects transport. So they're coupled both ways. So here is a list of applications that have used the physics framework that we just discussed, the poromechanics framework, transport with deformation in a porous medium. These have been used. I don't want to go through all of them. I just want you to see it's a long list that talks about what material or process, so that's a meat cooking, what are my driving force for deformation, so in this case it's swelling pressure, and what kind of constitutive model, what type of material model describes the meat, so in this case it was used as hyperelastic, and some specific details is modified neo-Hookean. We didn't get into these kinds of details here, but like that, there are other processes and materials that have been modeled using this kind of poromechanics framework. You can stop or pause the video and look through more of the details here. And then finally, so this is the last slide on the entire module of deformation. And here, I would like you to put a little bit of thought. I would like you to answer this question. You see these corn puff extruded products below. And I would like you to think of, as it's coming out of the extruder barrel, what are the driving forces for the deformation of these products? And what type of constitutive model would you use for these corn melts? I would like your thought on it. Please take your time and think about it, how you might be able to describe more this process, either qualitatively using the physics that you learned or quantitatively using a model. And you can include your response in the space provided on the website. So this concludes everything for the deformation module in our porous media framework.